Hello, my name is Paul Strotko, and I'm teaching a physics class. This is something that I've taught for physics students. They're learning about light. I'm teaching at Texas School for the Deaf in Austin, Texas. I also teach math. For the kids, it's 11th and 12th grade group of students I teach. All right, so now we'll get started. So, what is light? I plan to discuss all these items today. Where does light come from? The history of light. Where did light come from? Oh. Light speed. The comparison of light speed. Time comparison. And also talking about prisms. The electromagnetic spectrum. And then finally for the kids, we'll have different activities in class afterwards. And also they'll do their worksheets and a review. Okay, so what is light? We've always had the sun as the primary source. We've always had that. That never has stopped. Other common sources include flames, the fire, you see the light there. You also see here in the light the filament. We also have here plasma, and it emits a charge and the light glows from there. And also we have the sun via eclipse. Whenever the moon and the sun cover up one another, you get that sort of effect. Now for a brief history of light, I want to talk about that briefly. Yes, light does have characteristics of wavelength, frequency, it has velocity. And in 1905, Einstein, a very famous scientist, he published his theory saying that yes, light particles also has waves. And other scientists mentioned that too, and they are in agreement that yes, both light particles called protons and waves are together. And so let me show you what that looks like. This right here is a good animation for the audience to understand that we have the particles now, the protons, that are going through the glass. And throughout the glass, the particles change to waves as they go through that. You can see here. And so that's a good example of how scientists have, yes, definitely said that both particles and protons become the wave. So now we want to know about the speed of light. Is it slow? Actually, no, it's quite fast. It's 300 million kilometers per second. Okay, so I want to compare it to miles per hour. Kilometers per second versus miles per hour. So it's 187,500 miles per hour. So if you can imagine a car here going that fast? No. The light travels around the Earth 7.4 times in 1 second. Very, very fast. It's a thought that this just helps a kid realize, especially deaf kids, where they're able to see the pictures over the words. And so we can show this, give an opportunity to see a visual of what it looks like and how can light orbit 7.4 times a second. And so it really helps the kid understand, oh wow, it does go around the Earth. It's, of course, very fast in real life, but this is a slow demonstration of that. So now comparison of light speed, we'll go through this list. The fastest land animal is about 70 miles per hour, which is a cheetah. Now, the fastest airplane in the world at max is 2,000 miles per hour. Cannot go over that. So the fastest, quote unquote, breathable airplane in the world, they don't make this kind anymore. They've stopped making that. Now the International Space Station, the ISS, it orbits the Earth, is 17,500 miles per hour. And so now I want to ask why. Why do you think that is? You know why? On land or in the air, that slows down the plane. However, space, there's no air circulating up there. It's frictionless, so that's why it's able to go faster. So now when we talk about planet Earth and its speed of orbiting the sun, how fast? It goes 67,000 miles per hour. And so it takes 1 year for the Earth to orbit the sun, of course 365 days. So now if we talk about light speed, that still beats it. Now when we're talking about time comparison for light to travel to Earth, from the sun to the Earth, do you know how long it takes? It takes 8 minutes and 14 seconds. So altogether, 494 seconds. Is that slow? If you can understand that it's 100 million miles from the Earth to the sun, pretty fast. So now if you compare from the sun to the Earth, now if you look at the sun to Pluto and what the light travel speed is, it's much farther to Pluto. So how long it would take is 5.5 hours to go from the sun all the way to Pluto. It's 2.7 million miles. And so if the sun was gone, it would not even notice it happening until 5 hours later at Pluto. So our nearest star is the Alpha Centauri. And so it's not the brightest of all, but it's a bright star. It is the nearest. And now how long does it take for that light to get from the star to your eye? It's 4 years, which means it used to be that the star was over here and it's actually moved, and now we see the light at our eyes. It takes 4 years. That's a long time for light to arrive. So I would like to see how the light disperses. What is in the light itself? What's there? And you'll have an opportunity to see the different colors from the prism. So you see the white light as it's contained, and now as it goes in the prism, it's dispersion that happens. And you can see the various wavelengths. We have the blue, the true reds, the primary colors split off. Also here, each of them has a different wavelength. The red is the longest, the blue is the fastest. So it's 700 nanometers of a wavelength, which is actually 7 times 10 to the minus 11th meters, meaning very, very small micrometers. You can't see it. So to 4 to the 10 to minus 11th meters. You can see the different sizes of the wavelengths. It's a very slow wave with the red, getting all the way down to a faster wave with the violet. It has the different sizes. This is smaller, much larger with the red. And that's what the light, which you actually see, that spectrum. Just one moment. I'll give you a background of what this looks like. The electromagnetic spectrum. The light itself is energy that's emitted by accelerated electric charges often electrons and atoms is the way it happens. So that energy travels in a way that is partly electric and magnetic. And that's why it's called an electromagnetic wave. And so the range of the electromagnetic waves, let me show that to you. Right here. This is a chart to just help you see what it looks like. We have radio, it's a very long wavelength. And it, decreases all the way down here to the gamma rays quite fast. So long wavelength versus a faster wavelength. Now the colors that we were just talking about before falls right there on the spectrum. The others you are unable to see. So when you compare the wavelength, the frequency is 10 to the 4th, meaning it's 4 zeros. And you go all the way over here, 10 to the 20 means 20 zeros. Okay. Now comparing the waves, the size of a football field, if you can imagine, a very large area, all the way down to right here, which are subatomic particles. And if you use a radio, of course, this is an old AM radio versus a microwave here. And then we get over to the bioimaging. You see these pictures in the color spectrum. And then over here we see x-rays and now PET scans for the brain. And that gives you an idea of the different frequencies and what they look like. I want the students to just understand the difference between the three of these: frequency, velocity, and wavelength. Frequency, you understand that frequency, how you measure the wave, it's based on time of the wave right here. So that right there is the measure of it. 1 over time in what you call hertz. And it's true for electromagnetic spectrum, it's always true for the speed of light. At the speed of light, all of them. Velocity, they have a formula. Velocity equals wavelength size times frequency. And they give you an opportunity to see the meters per second. Then wavelength, which is lambda, which we've discussed prior. Lambda, it's a Greek term. Okay. Just to sum up the electromagnetic spectrum, radio to gamma waves that we know of, there are a lot more, but we haven't yet discovered those. We don't know yet what they are, but we do know radio to gamma waves for sure. Then frequency 10 to the 4th to 10 to the 18th hertz, wavelength of 10 to the 3rd to 10 to the minus 12th meters, meaning that 0.00000, 12 zeros. Sound is different. It's what's called a mechanical wave through material particles, through such as the air, and sound works with, for example, in space there's no sound, you can't, or there's no air, you can't hear. So oftentimes that's an issue there. Electromagnetic waves are not the vibration of materials, but vibration of pure energy. And always it's the same for the speed of light. So this is the review opportunity for students to review again, because they'll learn again and continue to practice those concepts. And we always give out the papers at the end, so you can do the worksheet. Once you're finished with that, you would do the lab. I hope you enjoyed this, and thank you.